So this is a video of a rope workout. I've never done it before, but I've heard that it's supposed to be a pretty tough workout and takes a lot of energy to do it. So we know that waves carry energy. The next thing we'd like to do is start to go through how do we talk about the energy of a wave, and we'll look specifically at waves on strings. So we know that waves transmit energy, and we know that's true. We can feel the heat of the sun. We know that waves on a beach, if you're standing in pretty heavy waves, that'll knock you over if you're just in a little bit of the ocean. If you're out somewhere like a concert and they're playing the music really loud, you can actually feel a bit of that vibration right in your bones. So we definitely know that waves transmit energy. And what we'd like to figure out is how much energy. Can we find an expression for that energy? So let's think about if something is moving with simple harmonic motion, and remember we are still dealing with sinusoidal waves. If something is moving with simple harmonic motion, then the total mechanical energy E is a combination of the kinetic energy plus the potential energy, and that amount of energy is constant. What we can do with this is if we wanted to find the energy of a wave, we could add a combination of kinetic and potential, or we could think about what if it had maximum kinetic, what would that mean about the potential, and what would it mean about the energy? Well, if it had minimum potential energy, if U is equal to 0, then all of the energy is kinetic. If all of the energy is kinetic, then the kinetic energy is the maximum kinetic energy. And maximum kinetic energy would be 1/2 times mass times maximum velocity squared. So if this were the case, then when we wrote down our energy, it would be 1/2 times m times V maximum squared plus 0. So this is an expression for the total energy of something moving with simple harmonic motion. And again, this is something that was covered in chapter 15, but this is a very quick recap. So let's apply this for any object moving in simple harmonic motion to a wave on a string. So the first bit we'll do is let's pick a little piece of that string. So here's a little piece of the string, and I'm going to say that this little piece of string I've picked has mass that I'll call delta M, and it has length that I'll call delta X. So the length from here to here would be delta X. We're talking about sinusoidal waves, so that waves which are produced by a sinusoidal source. That means every little piece of string is moving up and down in simple harmonic motion. Okay, so now we've set up for what we're going to do here. Let's write down, using this idea, what is the energy of that little piece of string. So an element of the string with length delta X and mass delta M moving with simple harmonic motion has energy E equals 1/2 times the mass times the maximum velocity squared. Something moving with simple harmonic motion, that's got an expression for velocity. Velocity is minus a omega cosine kx minus omega t plus phi naught. And the maximum velocity is a times omega. So that's the biggest the velocity can be. So let's plug this expression in back right here. So V max squared will be a squared times omega squared. Last thing we might want to do something with is delta M. Well, our linear mass density mu is mass over length, delta M over delta X. So that little bit of mass, delta M, is the mass density times the length, delta X. Let's plug that in for delta M. So this is the energy of one little piece of that string moving with simple harmonic motion. This is okay, but what tends to be a more useful expression, a more useful thing to think about, is the power. How fast is energy delivered? So let's ask, what is the power? And power is the rate of delivery of energy. So power is change in energy over change in time. So how fast the energy is being delivered. So the change in time of the expression that we just wrote here one half mu, a, and omega are all constants. How fast delta x, so how quickly along we're picking those different delta x's over time, that's just the wave speed. So then our power is 1/2 times mu times a squared times omega squared times the speed of the wave. And that's the power delivered by a traveling wave. So that's a pretty good part to have. We'll do another video with a couple more examples, and then that should clue up this lecture pretty well.